Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSC. So in this video, I'm going to discuss about question bank of graph roots. So explain cosine bridge problem. So the cosine burger is a city in the Pragal river in Prussia. So the city is going to be occupied by two islands plus areas on both banks of river. The problem is that so whether they could have leave home, so cross every bridge exactly once and return home. So that is the problem. So Cosine-Berg problem. So this bridge, the problem is going to be used or solved by make use of graph theory. So next one, define a loop and parallel edges. So the loop is nothing but an edge whose endpoints are going to be equal, and multiple edges means the edges is going to have same pair of endpoints. So then I can able to say that should be multiple edges. So illustrate about a simple graph. So a graph which is going to have no loops or parallel edges, then I can able to say that should be a simple graph. And the graph which is going to have multiple edges, I can able to call it as multi-graph, not a simple graph. Okay, a graph which is not going to have any loops or parallel edges or multiple edges, then I can able to say that should be a simple graph. And adjacent and neighbors. So the two vertices are adjacent and are also neighbors if they are going to have the endpoints of the edge. So in this graph, so A, B are adjacent here. So AD are not adjacent since there is no edges going to be connected between the vertices. And then discuss about finite and the null graph. So finite graph means a graph whose vertex set and edge set are finite. So that's why it should be a finite graph. And null graph means a graph whose vertex set and edges set are going to be empty is nothing but the null graph. So here, if I'm going to have a graph, we have vertex set. So this is the finite set of the graph, and this should be the edge set of the graph. So it should be a finite one, so that's why it should be called as a finite graph. Suppose if the vertex set is going to be null and edge set is also a null, then I can able to say that should be a null graph. Next one is define QQ and independent set. QQ in the graph is nothing but the set of pairwise adjacent vertices that should be called as a complete subgraph. An independent set in the graph is nothing but set of pairwise non-adjacent vertices. So example, if x, y, u is the QQ in the graph, so I can able to represent, and u, v, u, w should be an independent set. Okay. So x, y, and u. So this three is going to be form a collective, and u, v is nothing but an independent. So if I'm going to draw an independent set in the graph, so set of pairwise non-adjacent vertices is nothing but independent set. The next one, what is bipartite graph? So a graph is a bipartite. So if V of G should be the union of two disjoint sets called partite set of G. So here I'm going to have two kinds of problems like matching problem and then job assignment problem. So if I'm going to consider this matching problem, so I'm going to have a set of vertices and then set of another set of vertices. So where this should be comes under the boys group and where set of this comes under girls group. So here I'm going to have a mapping between the group of boys and a group of wolves. The mapping is going to be done in between the vertices, and the no vertex is going to have an edge among this group. Then I can able to say that should be the bipartite graph. So similarly, if I'm going to have an assignment problem here, so in this I'm going to have a set of vertices that should become under workers, and here also going to have a set of vertices that should become under the jobs. So I have to map the vertices among the edges of the vertices. So what I'm going to do, so I have to assign the jobs to the workers here like this. So I'm not going to map an edge in between this set of vertices and this set of vertices here. So this all not possible in bipartite graph. And next one is chromatic number. So chromatic number of the graph is going to be represented as x of g. So that should be the minimum number of colors that are going to be needed to label the vertices, so that the adjacent vertices is going to be received different colors here. Okay, so if I'm going to have a graph like this, so in this graph, so I want to assign the colors, so in such a way that so that no two colors is going to have should not coincide with each other. Suppose if I'm going to map this vertex is blue color, then have to apply green here, right? So here if I'm going to have like this, I'm going to assign another color here that should be treated as red. So what color I have to assign here? So if I'm going to consider blue, so the blue, these two nodes are going to be coincide. And similarly, if I'm going to assign red, these two nodes are going to be coincide. And if I'm going to consider this one, green, so these nodes are going to be considered. So that's why I have to go for another color in between that. It will be pink. So what color I can able to assign? So I can able to assign here either red, or I can able to assign blue also, so that these two nodes are not going to be coincide. So that's why. So I'm going to take this should be as red. I'm going to consider. Okay. So the chromatic number means that so the minimum colors that are required to color the vertices of the graph, and that thing should be represented as x of g. And next one is explain about map coloring. So the map is a partition of the plane into two connected regions. So here we can able to color the regions of every map using at most four colors. So this map coloring is also same as graph coloring. So in map coloring, so the regions are going to be considered as the vertex, and adjacency of the regions are going to be considered as the edges. So if I'm going to have a map like this, so this is the one vertex I'm going to consider, and this is the under vertex. This is the under vertex I'm going to consider. So the path what is going to have, so that should be considered as the edge here, and I'm going to map color this region with some other, and I'm going to be color this region with some other color. So this and all the edges I'm going to be considered, that should be the boundaries of the region, and here also, and these regions are going to be considered as the edge. And next one, what is the path and cycle? So the path is nothing but the sequence of distinct vertices such that the two consecutive vertices are going to be adjacent. For example, ADCBE is the path, and suppose I'm going to have, so in this graph, so ADCBE. So this is the one of the path of that. So in the graph, I'm going to have different types of paths. What I'm going to say. So suppose, so one path is that, so A to B, B to C, C to D, and E to E. So another part also I can able to get it as A to B, B to E, E to D, D to A. So this is another path, and A to E, E to D, D to C. So like this, we're going to have different kind of paths here. So here, the path what I'm going to say like so A to B, B to E, A to D, D to C, again C to B, C to E. So the path what I mentioned, so I should not be called as a path. So it should be called as a walk here. Okay. So what is the difference between this path and then walk is that? So if I'm going to consider the path, so all the vertices are going to be unique, whereas in walk, the vertices are going to be repeated in nature. That is the difference between the path and the walk. And cycle means so the path which is going to have the source, vertex, and then destination is same. I can able to say that should be called as a cycle here. Okay. So whenever the source and destination vertex in the path is same, then I can able to say that should be a closed path. I can able to call it as a cycle. So if I'm going to consider the vertex like A to D, D to C, C to B, B to E, and E to E. So the source is same and also destination is also same, right? So that's why I can able to call this should be a closed path. And discuss about subgraph. So subgraph of the graph is a graph H such that so the vertex set of the subgraph should be subset of the vertex set of original graph. Similarly, the edge set of subgraph should be subset of edge set of the main graph. Suppose if I'm going to have a graph like this, so A to B, B to C, C to D. So here the vertex set is that so A, B, C, D, and the edge set is that E1, E2, E3, E4, E5, and E6. Right? So if I'm going to consider this part of this graph, so I'm going to consider some part of the graph. So what is this? Let it be graph G. And here if I'm going to have E1, E5, and then E2, and edge set should be, oh sorry, this should be the edge set. And the vertex set is that, so A, B, D. So right, so let it be H. So the edge set and vertex set of the subgraph should be subset of this graph, right? So then only I can able to say the graph should be the subgraph. So here I'm going to have some other different types of representations of the graph, like so. This should be the original graph G, and here in this one, so some part I'm going to consider like AD. So sorry, DC. So this is also a subgraph, and this is also a subgraph, and this one and this one is also a subgraph. Okay. So next one is the what is the connected and disconnected. So connected means so there exists at least one path between the pair of vertices, and disconnected means it should be otherwise. Suppose if I'm going to have the graph like this, so H1. So what is this H1 and H2? So H1 and H2 are said to be connected. So because the edges are going to be connected for each and every vertex of the graph. So when it comes to H3, so there is no connection between A to B and then E to E. So these two are the two different subgraph which is not going to be connected here. So that's why it can able to call this should be called as a disconnected graph. And next question is that discuss about adjacency matrix. So here, if I'm going to have the vertex set and edge set of the graph, and mod v is nothing but the number of vertices in the graph, and mod e is that should be number of edges in the graph. So how are we going to represent a graph in the form of adjacency matrix here? So if I'm going to consider a graph here, so set of vertices are going to consider along the rows and set of vertices also consider along the columns. So here what I'm going to say, so whenever there exists an edge from uh, one vertex to another vertex, so here I'm going to have an edge from W to X, so that's why I'm going to represent it as 1, and W to Y also there, so I'm going to represent it as 1. So similarly, if I'm going to consider X in this case, so I'm going to have the vertices edges from X to W, X to Y. So X to Y should be 1, but I'm going to have two parallel edges that are going to be connected from X to Y, so that's why I'm going to present it as 2 in this case. So similarly, if I'm going to consider Y, so I'm going to have the edges W to Z, and I'm going to have two edges that are going to be connected to X, that's why it should be 2. And next one, what is an incidence matrix? So incidence matrix is nothing but so it should be also n by n matrix, where it is going to have ones and zeros, but the mapping is going to be done along the vertices and the edges. So what are the vertices in the graph? I'm going to consider it as the rows wise, and the edges what are present in the graph I'm going to consider along the column wise. So if I'm going to have the vertex W, so what are the edges that are connected from W, A, B? So that's why I'm going to represent 1. So remaining all should be 0. Similarly, if I'm going to consider Z, I have edge only E, so that's why I'm going to represent 1. So similarly, if I'm going to have X, so X in this case I have an edges from X to W, X to Y. So I have edges like A, C, and then D. So I'm going to represent that should be 1. So remaining all should be zeros. So the adjacency matrix is going to be mapped between the vertices and vertices. So whereas the ancient matrix, the mapping is going to be done between vertices and then edges. And next question is that, so explain of isomorphism. So isomorphism of the simple graph is a bijection. So that is going to be represented as the function v of g tends to v of h, such that uv is going to be belongs to the edge set of the graph. So if and only if f of u and f of v should be belongs to e of h. So let us consider, so this is the graph h, g, and this is the graph h. The function is going to be f1, and this is the other function I'm going to be defined. So then only I can able to say these two graphs are said to be isomorphic graphs. And next one, so discuss in detail about complete graph. So complete graph means, so a graph whose vertices are going to be a pairwise adjacent. Suppose if I'm going to have a graph of 3 vertices, so I have the vertex from v1 to v2 to and v3. Similarly, if I'm going to consider v2, I have an edge from v1 and v3. So if I'm going to consider v3, I have an edge from v1 and v2. So then only I can able to say that that should be the complete graph. So a graph which is going to have multiple connections. At the same time, I can able to say, so for every pair of vertices, I have an edge connected between them. And next one is what is complete bipartite graph here. So the complete bipartite graph is a simple bipartite graph such that, so the two vertices are going to be adjacent if and only if they are in different partite sets. So just now I said I'm going to have a set of vertices, and I'm going to consider these vertices based on some feature. So I'm going to have, so A, B, C, D, E. So this should be A, C, E, and B, and then D. So I'm going to segregate this set of vertices into two different set of vertices, and I'm going to be map in between this pair of vertices. So then only I can able to say this should be the complete bipartite graph. And next one, discuss about the path and its components. So what is the path? So the u comma v is the path, or u comma v is nothing but the trail of the vertex u and the last vertex v, and these are going to be endpoints. So uv, the set of trail of vertices which is not going to have no repeated vertex, then it should be nothing but the path. And the length of the path, trails, path or cycle is nothing but the number of edges that are present in the path. And a walk or trail is nothing but close if the endpoints are going to be same. So okay, so in the path no repeated vertex is going to be occur, whereas in walk we can able to have the repeated number of vertices, and that should be closed path or maybe a closed walk also. So what is the component? So the components of the graphs are the maximally connected subgraph, and the component or the graph is a trivial if it is going to have no edges. Otherwise, it should be non-trivial. Okay. So an isolated vertex is the vertex of degree 0. Then discuss about Euclidean circuits. So what is then Euclidean circuit? So a graph is said to be Euclidean. So if it is have a closed trail containing all the edges, and we can also call the closed trail a circuit when we not specify the first vertex, but we have to keep the list of cyclic order. So the Euclidean circuit or Euclidean trail in the graph is a circuit or trail containing all the edges of the graph. Okay. So a graph is said to be Euclidean or Euclidean if it is going to have a closed trail containing all the edges. And we have a closed trail called as a circuit. So when we need not to specify the first vertex, but we have to be keep the list in the cyclic order. And what are the weakly and strongly connected graphs? So a graph is weakly connected if it is underlying a graph is said to be connected. And a digraph is strongly connected if and only if for each pair of ordered pair of vertices there exists a path from U to V. Then discuss about Euclidean graphs. So Euclidean digraph means Euclidean trail in a digraph, as the graph is a trail containing all the edges, and Euclidean circuit is nothing but a closed trail containing all the edges, whereas the digraph is Euclidean if it is going to have Euclidean circuit. So Euclidean trail and Euclidean circuit. So these are the two terminologies. And a graph is said to be Euclidean if it is going to have the Euclidean circuit. So what is the difference between this Euler circuit and Euler path? So whenever the graph is going to have no vertices of odd degree, then I can able to say that should be Euclidean circuit. So when the graph is going to have exactly two vertices of odd degree, then it is going to have at least one Euler path. And when the graph is going to have more than two vertices of odd degree, then there is no Euler circuit or no Euler path, and there is no possible where we can able to travel along the vertices, where we can able to travel along the edges of the graph without having to cross some of them more than once. So these are the different types of Eulerizing the graphs. So here what I'm going to say is, so there should be a step-by-step process in order to achieve this Eulerizing the graph. So the first step is to have to identify the odd vertices, and second step we have to be add the duplicate copies of the edges to create all the even vertices. Then only you can able to make this graph as a Eulerizing graph. And semi-Eulerizing. So in semi-Eulerizing, we have to be identify the odd vertices, and second step we have to be leave out the two odd vertices and have to make the add duplication of the edges to create the even vertices. And what are the applications of this graph? It should be mainly used in Chinese postman problem and communicating networks, and I can also going to be used in list guide. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.